Hello, I am Zaid Memon, captain of team NAW. NAW is an undergraduate student team based in Karachi, Pakistan that designs and manufactures unmanned aerial systems. The team emerged as the grand champions of IMECI US Challenge 2019 and was runner-up for the same in 2021. This year, we're participating in international pre-mission UAV competition, Technofest. Our mission consists of a swarm of hexacopters that are deployed for a search and rescue operation. The drones have to search for markers placed on ground efficiently and deliver payloads to each ground marker. Our implementation of the system makes it so that the system is completely decentralized, meaning there is no ground control station. It is invariant to the number of drones and to the size or shape of the search area. And most importantly, the system is completely autonomous.
For research and rescue operation, we have developed a system that utilizes a swarm of unmanned aerial vehicles to effectively look for search targets by scrutinizing their surroundings in a coordinated fashion. A multi-drone system has been adopted as it is efficient, reliable, and robust. The system is decentralized and the drones are piloted by companion computers that will run the entire swarm network by shutting down in case of any mishap to a central command center. An area division algorithm has been developed that divides the area equally and assigns them to the drones to carry out a collision-free search operation in minimum time. A survey algorithm follows that enables the UAVs to inspect their respective areas for ground minders. Throughout the mission, the drones remain in sync via an encrypted mesh networking protocol, ensures secure and reliable transmission. The design is easily scalable. With slight modification, the system can be adapted for a wide array of tasks such as search and grab, commercial photography, aerial mapping, and geophysical surveys.
We chose hexacopters as the multi-rotor configuration since they offer greater stability, last longer, and can carry heavier payloads. The flight controller chosen was Pixel Cube, and the companion computer being used is Raspberry Pi 4B. The GPS system being used is Air3, a high-precision GNSS system. Drones communicate using the Zigbee protocol provided by DXPs. The camera being used is a 720p Logitech C310, which has proved to be adequate for our use. Certain changes have been made since the last submission to cut down on our expenditure. Firstly, switching from Jetson Nano to Raspberry Pi 4B as a companion computer due to the scarce availability and high prices of Jetson Nano. Secondly, we dropped from 3 drones to 2 drones due to the high total cost of the required equipment. Thirdly, the 3D printed plate from the bottom of the hexacopter is now attached to the top for ease of assembly. Fourthly, a new payload mechanism has been designed and attached to the bottom plate. Fifthly, the gimbal has been removed. Sixthly, the position of the electronics component has also changed for better CG balancing.
After a brainstorming session, we designed the model we had purchased and its components. Then we put each component in its proper position for ease in assembly process and to get the desired location of center of gravity we wanted. Center of gravity lies exactly at center as plane. We also modified the model according to our requirements, as there isn't enough space on 2 plates to house the hardwares. So we designed an extra 3-dimensional plate of 70% infill polylactic acid and SolidWorks. Takeoff mass is around 2.5 kg. To release the payload, we use a servo-actuated payload drop mechanism that operates with one servo motor and uses 3 links to convert circular motion of servo to translated motions like a slider crank mechanism to drop the payload of 100 grams. When UAV approaches drop zone, Pixel will actuate the servo which moves the push rod and releases the payload. After designing, we perform a structural analysis on the frame of hexacopter. For a hexacopter, the frame is the main load-bearing component. Meshing resolution used is fine to get the accurate results. When we apply 20 Newton of thrust on each motor, the displacement is just 3.29 mm and there is very little strain. The maximum equivalent stress that is obtained is 11.5 MPa as shown. The ultimate tensile strength of the frame material is 120 MPa. Then we conducted a static structural analysis on the upper plate of hexacopter. When we apply a force of 10 Newton on the top plate, we see a very little deformation. Top plate material PLA has an ultimate tensile strength of 42 MPa. The obtained maximum equivalent stress is only 0.5 MPa as shown in figure. As a result, the 3D printed plate can safely bear the stress. In order to check the reliability of payload drop mechanism to carry 100 gram payload, 1 Newton of force has been applied on the push rod. It's found that very small deformation occurred on the push rod. The results obtained are within the limit when compared to the tensile strength of material. Stress on housing of servo is also very minimal, hence the payload drop mechanism is safe to use and can withstand payload weight.
The team has chosen to procure a ready-made frame 30% glass fiber reinforced PA66 frame which also has high strength, rigidity, creep strength and dimensional stability and carbon fiber T-type landing gears. We modify it according to our requirements. An extra 3-dimensional plate was designed in SolidWorks and 3D printed with 70% infill PLA polylactic acid, as there isn't enough space on two plates to house the hardware. The payload release mechanism also consists of a 3D printed housing and is attached to the lower plate of the hexacopter. 4 holes were drilled for M3 bolts in servo housing as well as plate.
The DJI F50 consists of carbon fiber PCB frame board screwed at the top and bottom of the PA66 GF30 arms. The landing gear and payload release mechanism is attached to the lower plate. The top 3D printed board is used for mounting battery and GPS. In middle space we place Pixhawk. The heart of our UAV system is the Pixhawk Cube, black. It is the flight controller for the UAV and controls all flight parameters. It connects to various fundamental components of the UAV including propulsion system, BLDC motors, payload drop mechanism, single board computer Raspberry Pi 4B, GPS system along with XP modules for communication purposes. The UAV is powered by a lithium polymer battery with a 3S configuration. The battery is connected to a PDB power distribution board from which the Pixhawk motors and Raspberry Pi are powered. In the lower section we place Raspberry Pi single board computer and their XP modules.